So picture this, right? It is 2 a.m. on a Tuesday, and your pager just starts absolutely screaming, ripping you right out of a dead sleep.
Oh, yeah, the classic IT nightmare scenario.
Exactly. You are the CTO or maybe the lead developer or, just the poor person holding the bag for a product that generates literally 100% of your company's revenue.
Right, and you check your phone, and it's just a wall of alerts.
A massive cascade of 500 internal server errors. So you scramble to your laptop, your eyes are burning, you pull up the logs, and here is the kicker. It is not a bug in your code.
It never is in these scenarios, is it?
No. The cloud provider hosting the AI model that your entire backend is hard-coded to talk to, well, they just deprecated that specific legacy version.
Just turned it off.
Yep. No warning email, no grace period. They just needed room on their servers. So you are officially offline, hemorrhaging cash, and you are going to stay offline until your engineers completely rewrite your core logic to speak to a totally new API.
Which is terrifying because in the current market, that isn't just a hypothetical ghost story. It is an inevitability.
So today, our mission for this deep dive is to make sure that Tuesday night never happens to you.
We have to fix the architecture.
Right, because we are looking at this digital foundation you rely on every day, and we have to confront a really uncomfortable truth. You do not own your workflow.
You really don't, and people hate hearing that.
Okay, let's unpack this, because we assume that when we write code and connect an API, digital concrete is being poured. Like, if I integrate Stripe into my app, Stripe isn't going to suddenly deprecate the concept of a credit card without giving me 5 years of notice.
Right, the traditional SaaS world is stable. But the AI ecosystem of 2026, that concrete never actually sets.
No, the ground is just constantly shifting. Prices spike, models die, companies pivot. So we are examining a stack of really vital sources today, including some technical blueprints, a 2026 AI API pricing guide from Cloud Insight, LiteLLM documentation, and this huge Ollama update to build what we are calling the AI exit ramp.
I love that term, the exit ramp.
We want to design a vendor-resilient workflow that doesn't just survive this chaos, but actually thrives on it.
And this requires a fundamental shift in how we think about building software.
Yeah.
Because, visualize the current market like a really stormy, volatile digital landscape. For the last few years, the default has been to build your business around a specific AI product.
Like wrapping your whole company around OpenAI or Anthropic.
Exactly. You mold your data to fit their specific context window. You write your prompts to appease their unique safety filters, and you basically lock all your business logic inside their proprietary SDKs.
Which feels safe at the time.
It does, but we have to stop doing that. We have to start building systems capable of using interchangeable AI products as raw commodities. Because if you don't control the exit ramp, you are basically a hostage to your vendor's next board meeting.
Yeah, that's a brilliant way to put it. You're a hostage. And to build that exit ramp, we first really need to understand the exact nature of the threat.
We need to shatter the illusion of stability.
Right, because these platforms are not stable utilities like AWS or Google Cloud Storage. Let's look at the sheer financial volatility we've seen recently. The pricing data circulating from 2024 to 2026 it's just wild.
It's unprecedented, really. Just look at the Sonnet price spike.
Oh man, yeah. Let's talk about Claude Sonnet 5.
That is a perfect case study in why hard-coding a single vendor is so dangerous. So when Anthropic introduced Sonnet 5, they priced it really aggressively to capture market share. Right?
Super cheap. It was, what, $2 per million input tokens?
$2 for input and $10 per million output tokens.
Sure.
And developers flooded in. Startups calculated their unit economics based on those exact margins, and they built their entire product roadmaps around it.
And then the introductory period ended.
It sure did.
On September 1st, 2026, the price just jumped. It went to $3 for input and $15 for output.
Right. An immediate 50% cost increase, literally overnight.
That is brutal.
Now, imagine your startup was operating on thin margins, and your code base was tightly coupled to that Anthropic API. Your cloud bill just spiked 50%.
And you have absolutely no recourse.
None. You couldn't easily switch to a cheaper competitor because your prompts were heavily optimized for Sonnet. Your data parsing relied on Sonnet's specific JSON format.
Your engineers would need weeks to refactor everything.
Exactly, so you just had to eat the cost.
I can hear the counter argument from some developers right now, though. They'll say, okay, prices fluctuate, but eventually these models stabilize.
But they don't stabilize.
No, they just get taken out, back and shot. I mean, the graveyard of deprecated models is massive.
It really is.
Look at Google's Gemini 2.0 Flash. It was the absolute darling of the developer community for lightweight tasks. Deprecated in February, and then completely shut down and purged from the servers by March 3rd, 2026.
Yep. Claude Haiku 3 and 3.5 on Vertex AI suffered the exact same fate.
If you were routing production traffic to those endpoints are now just dead links returning 404 errors.
And we really have to unpack the mechanics of why this happens, because it explains why this volatility isn't going away anytime soon.
It's all about the compute, right?
Exactly. It comes down to the brutal economics of compute. Hosting these massive neural networks requires clusters of specialized GPUs and TPUs.
Which are insanely expensive.
Tens of thousands of dollars apiece. And they draw massive amounts of power.
Mm.
A provider like Google or OpenAI literally cannot afford to keep a fleet of expensive servers running an outdated model from 2 years ago just because a few enterprise clients haven't bothered to update their code base.
It's a waste of their hardware.
Right. Every server running a legacy model is a server that isn't running their shiny new flagship model. So they routinely purge the old to make room for the new.
Okay, so the lifespan of a model is inherently short, but it's not just the fear of a model disappearing, is it? It's the absolute chaos of how these models are priced relative to each other today.
The spread is massive.
When I was looking at the recent enterprise pricing breakdowns from Cloud Insight, I found a metric that completely blew my mind. There is literally a 100x gap in pricing for doing the exact same computational work.
It is the most critical metric for any engineering league to understand. You don't see spreads like this in traditional cloud computing.
Let's lay out the actual numbers for you guys. If you look at API input costs today, you have Google's Gemini 2.5 flashlight sitting at 10 cents.
10 cents per million tokens.
Right. On the total opposite end of the spectrum, you have Anthropic's Claude Fable 5, which costs $10 per million input tokens.
That is literally a 100x multiplier.
100 times more expensive just to read the text. And remember, the output tokens, the text the model actually generates, are universally 2 to 5 times more expensive than the input.
Which means if your application is routing every single user request, even really simple things like formatting a date or classifying a support ticket to a premium $10 model, when a 10-cent model could achieve the exact same accuracy.
You are incinerating your runway.
You're just burning cash for no reason.
But wait, I have to challenge this comparison a bit because I know it's not just a straightforward numbers game. We can't just open a spreadsheet, look at the per million token cost, and assume it's a perfect apples-to-apples comparison between OpenAI and Anthropic.
Ah, right. You are talking about the tokenizer trap.
Yes, the tokenizer trap. Let's break down how this actually works at the architectural level, because this completely warps the financial math.
It really does.
For anyone not deep in the natural language processing weeds, let's establish what a tokenizer physically does.
Okay, so at a fundamental level, a large language model does not understand human words.
It just sees math.
Right, it only understands arrays of numbers. A tokenizer is the algorithmic translator sitting at the front door of the API. It takes your string of human text and chops it up into subword chunks.
And those chunks are the tokens.
Exactly. It assigns a specific integer ID to each chunk. Historically, the rough heuristic in the industry has been that 1,000 tokens equal about 750 English words.
But, and here is the trap, that heuristic assumes everyone is using the exact same dictionary to chop up the words.
And they absolutely aren't.
Right. OpenAI uses a specific byte pair encoding algorithm, usually accessed via their tick token library.
But Anthropic, for their newer models like Opus 4.7, Fable 5, and Sonnet 5, deployed a completely proprietary, heavily modified tokenizer.
So it algorithmically chunks the text differently.
Yep. It might split a complex medical term into 4 tokens, whereas OpenAI's tokenizer only splits it into 2.
Wow. Okay, wait. So comparing these APIs is like buying a car where the dealership decides to change the size of a mile after you drive it off the lot?
That is a brilliant way to look at it. Let's look at a practical example.
Okay, lay it on me.
Say you take a massive 10,000-word legal contract and send it to OpenAI. Their tokenizer might process that payload and bill you for roughly 13,000 tokens.
Okay, 13,000 tokens for OpenAI.
Right. But if you take that exact same file, byte for byte, and send it to Claude Fable 5, the metrics show their new tokenizer produces roughly 30% more tokens for the exact same string of text.
Wait, really? 30% more?
Yes, so suddenly, your 13,000 token payload is being billed as 17,000 tokens.
That is nuts. Your warranty expires 30% faster just because of how they count.
It is a brilliant and honestly somewhat insidious way to increase revenue without changing the sticker price on the marketing page.
Seriously.
Even if Anthropic dropped their list price per million tokens to perfectly match OpenAI, you would still be paying 30% more per API call simply because of how the tokenizer inflates the volume.
Meaning you cannot optimize your workflow purely on advertised token prices. You have to measure the holistic cost of completing a specific task.
Exactly.
Okay, I see the financial trap, but let me push back a bit. Let me play devil's advocate here.
Go for it.
I know engineering teams who look at all this volatility, price spikes, the deprecations, the deceptive token counting, and their conclusion is actually the exact opposite of what we are arguing for today.
Oh, I know what they say.
Right. They say, look, managing multiple vendors is an engineering nightmare. OpenAI has GPT 5.6 Sol, which benchmarks highest on almost every reasoning task. Why not just go all in? Isn't it just easier to stick with OpenAI if they have the best models?
They want to use the custom SDK, the proprietary agent frameworks, build deep loyalty, and just accept the risk.
Yeah, the engineering simplicity is worth the vendor lock-in to them.
I hear that argument constantly.
Yeah.
And it is a incredibly seductive trap because it is the path of least resistance.
It's so easy to just type import OpenAI.
Exactly. It allows a developer to build a prototype in an afternoon. But we really have to distinguish between building a prototype and maintaining enterprise-grade software.
Right.
When you build deep loyalty to a single vendor, your loyalty does not insulate you from their operational failures.
They don't care how much you love them if their servers are down.
Precisely. If OpenAI suffers a massive multi-day localized outage, which happens to every major cloud provider, your customers do not care about your vendor loyalty.
No, they only care that your application is returning a blank stream.
Your uptime is entirely tethered to a company over which you have zero board seats and zero leverage.
Which brings us perfectly to how we actually architect our way out of this trap. If we agree that hard coding an API is a ticking time bomb, how do we structure an AI-integrated business to actually survive?
We need to evaluate workflows across 3 distinct architectural paradigms.
Okay, let's break them down.
The first paradigm from the evergreen topic source is what we call the fragile architecture. This is the exact scenario you just described. The flow is strictly linear.
So business application connects directly to one AI provider, which handles everything.
Exactly. You import the Python library, you put your API key in the environment file, and you hard-code that client call directly into your main application loop. Every single user prompt flows through that one specific pipe.
It's a glass house.
It is. If that pipe clogs, or if the toll to use that pipe triples, the entire house shatters. You have zero optionality.
So we move to the next evolution, which is the better architecture.
Yes, this is where we introduce a critical decoupling.
The business application connects to a workflow layer, and that workflow layer connects to a roster of replaceable AI models.
This is where we start seeing real engineering maturity. You are no longer calling the vendor directly. You are calling a middleware system that you control, and that middleware routes the traffic based on logic that you define.
Okay, but the ultimate destination, the holy grail we're aiming for, is the resilient architecture, right?
Yes. This is a much deeper paradigm shift.
This looks like the business application connects to completely owned data wrapped in open formats, which plugs into the workflow layer, which can then seamlessly route out to cloud AI providers or dynamically route down to local on-premise AI models.
Or even models that haven't been invented yet. This is true digital sovereignty.
But achieving it isn't just about throwing a proxy server in the middle of your code and calling it a day, is it?
No, not at all. You have to audit every single layer of your application stack to ensure you aren't secretly logged in. What's fascinating here is that vendor independence doesn't mean avoiding vendors. It means being able to replace one without rebuilding your entire business.
We have a framework for this, right? The AI portability audit.
Yes. It forces a team to examine 5 distinct layers: data ownership, prompt portability, model portability, integration portability, and recovery.
Let's actually walk through an audit right now, because I think a lot of teams assume they are portable until they actually look under the hood. Let's start with prompt portability and data ownership because they are so heavily linked.
That's a great place to start.
If I am an engineering lead, what exactly am I looking for here?
You are looking for where your intellectual property physically resides. Ask yourself, where are the system prompts that define your AI's behavior?
Oh, I know where this is going.
Are your engineers logging into a vendor's web interface, like an OpenAI custom GPT builder, or Google's Vertex AI console, and typing those carefully crafted instructions directly into a proprietary text box?
Oh, man. I know enterprise teams who have spent literally thousands of hours meticulously refining a 5,000-word system prompt. It acts as the entire persona and reasoning engine for their customer service agent.
And it lives exclusively inside a text field on a third-party website.
Yep.
If you are doing that, you do not own your business logic. The vendor owns it.
That is so dangerous.
If they lock your account or if they decide to sunset that specific builder tool, your intellectual property vanishes into the ether.
So how do we fix that?
Achieving prompt portability means treating your prompts as production source code. They must live in a Git repository, version controlled, as standard text or markdown files. Your application should pull the prompt from your own repository, inject the user's variables into it dynamically, and then fire it off to the AI.
That just makes total sense from an engineering hygiene perspective.
Yeah.
And this concept extends to the actual source data, too, specifically when we talk about RAG systems, right? Retrieval Augmented Generation.
Yes, the data ownership layer is absolutely critical in RGE. For any listeners unfamiliar, RGE is how you give an AI a memory of your specific company data.
You take all your internal wikis, PDFs, customer logs.
Right. You convert them into mathematical vectors, and you store them in a database. When a user asks a question, the system searches that database for relevant information and feeds it to the AI.
The trap here is where that vector database lives.
Exactly. The trap is using a closed proprietary cloud service that ingests your raw documents, automatically converts them to vectors using a black box embedding model, and doesn't give you a clean, raw export of the mathematical embeddings.
You're stuck in their ecosystem.
You want your source files in plain text, markdown, or standard JSON. And you want your embeddings stored in a system where you can easily dump the entire database and spin it up on a different server tomorrow.
You know, it is the casino chip analogy all over again.
Oh, I like this.
A fragile architecture is like walking into a massive casino, trading all your life savings for their specific branded plastic chips, and then just leaving those chips in your pockets for years.
You feel wealthy.
Exactly. You feel incredibly wealthy. You can play high-stakes blackjack. You can buy expensive drinks at their bar. You feel like a high roller. But the second you try to walk out the front door and buy a sandwich at the grocery store across the street, you realize you are actually broke.
Because you have zero liquidity.
Right. If the casino suddenly changes the payout rules of blackjack, you are completely trapped because your wealth only exists within their walled garden.
That is a phenomenal way to visualize it.
Yeah.
Vendor independence does not mean you refuse to play at the casino. You absolutely want to leverage the state-of-the-art models from Anthropic and Google.
But you want to hold cash.
Yes. Independence means you can cash in your chips at 2 a.m., walk across the street to a competitor's casino, buy their chips, and resume playing your game without missing a single hand.
Okay, I buy the philosophy completely, but now we really have to talk about the actual execution.
How?
Yes. How do we build this workflow layer to achieve model portability? I want to stop writing direct SDK calls to OpenAI. I want to build the middleware. What is the mechanism?
This is where we dive into the abstraction layer, and specifically, a piece of open source technology that has become the foundational routing engine for resilient architectures.
We're talking about LiteLLM.
LiteLLM, yes.
Here's where it gets really interesting because this is intensely practical. Let's define what this tool physically is. LiteLLM is an open source Python SDK, but more importantly for enterprise deployments, it runs as a standalone reverse proxy server.
Right. Its entire job is to act as a universal real-time translator for API requests.
To understand the power of this, you really have to look at how the industry developed over the last few years.
OpenAI was first to market with a highly usable API. Consequently, their specific JSON request format, the exact shape of how you send a message, define a role, and request a response, became the de facto standard.
Thousands of applications were hard-coded to expect the OpenAI format.
And then competitors like Anthropic and Google showed up with incredible models, but entirely different, highly complex API structures.
If you wanted to switch from GPT-4 to Claude, you had to rewrite your entire networking layer to handle Anthropic's unique way of formatting system prompts and message arrays.
Exactly. LiteLLM solves this at the network layer. It tells developers, do not rewrite your code. Keep using the exact OpenAI format you already built. But instead of pointing your network request to the OpenAI API, you point it to your internal LiteLLM proxy server.
So the proxy receives a payload that looks exactly like an OpenAI request.
Yes. And then in milliseconds, LiteLLM intercepts that payload, reads your configuration file, and maps that standard request to over 100 different AI backends.
100? That's wild.
Over 100. Anthropic, Gemini, Azure, you name it. If you tell it to route to Google Gemini, it intercepts the OpenAI-shaped JSON, translates it natively into Google-specific REST architecture, signs it with your Google credentials, fires it off to Google, receives the response, translates it back into the OpenAI format, and hands it back to your application.
It is the ultimate international power adapter.
Oh, exactly.
You travel across Europe, Asia, South America, and every single country has a bizarre proprietary wall outlet. But you have this one massive heavy-duty adapter block. No matter what the voltage or the pin layout is on the wall, you just plug your hairdryer into the standard US plug on the back of the adapter.
And the hairdryer just powers on.
The hairdryer, which is your application's core logic, is completely oblivious to what country it is physically operating in. But how does it know when to switch?
Well, just like a travel adapter centralizes your electrical safety, the proxy container centralizes your security and key management. You no longer have developers scattering 50 different API keys across different microservices.
Oh, that's a huge security relief.
It is. The LiteLLM proxy sits securely in your infrastructure, holding the credentials for Azure, AWS Bedrock, Anthropic, Google. Your application only needs to know one single internal endpoint and one internal key.
But the translation engine is just table stakes, right?
Yes, the true enterprise-grade superpower of LiteLLM, the feature that actually keeps you online during a Tuesday night outage, is its fallback engine, or provider failover.
Let's dig deep into this because this is where the resilience becomes automated. A fallback mechanism means that if your primary AI provider drops a connection, times out, or throws a 500 error, LiteLLM doesn't just pass that error back to your user and crash the app.
It automatically catches the failure and silently reroutes the exact same request to a backup provider.
It is a self-healing network topology.
And you configure it in a simple YAML dictionary. You define a primary model, or you define a number tries integer, let's say 3.
So if the primary fails, it tries again 3 times.
Right. And if it hits the retry limit, it instantly cascades down to a secondary model group you've defined. The end user simply experiences a slight increase in latency, but the application never crashes.
But looking closely at the system architecture and the documentation, it is not just a blind generic catch-all net. The routing logic is highly sophisticated. There are 3 specific types of fallbacks built into the code base that handle totally different failure states. Let's walk through them.
Sure. Let's start with content policy fallbacks.
Yeah, how does that one work?
This specific fallback is critical if you operate in enterprise environments or highly regulated industries. Every major AI provider employs opaque, proprietary safety filters and content moderation models that run in parallel to the main LLM.
And these filters are notoriously erratic.
They really are. You might send a prompt containing standard legal text or medical terminology, and Microsoft Azure's strict moderation layer might falsely flag it as a policy violation and block the request.
Returning a specific content policy error count.
Exactly. In a fragile architecture, your app just breaks, and your user gets an inexplicable error message.
But with LiteLLM, you configure content policy fallbacks. So when the proxy detects that specific policy error code from Azure, it knows the model isn't broken, the network isn't down, but the prompt is just blocked.
Right. So it dynamically reroutes that specific payload to an alternative provider, perhaps Anthropic or an open source model, whose moderation filters might evaluate the nuance of the text differently and actually fulfill the request.
You are essentially playing the provider's safety algorithms against each other to guarantee uptime. That is an incredibly clever engineering hack.
It's extremely effective.
Okay, the second specific fallback type is context window fallbacks. This one fascinates me because it operates fundamentally differently. It intercepts the error before it even happens.
This is entirely about network efficiency and cost control. Every model has a hard ceiling on its context window, the maximum amount of tokens it can hold in its memory for a single request.
Right, some older legacy models max out at 16,000 tokens, while newer models can handle 1 million or 2 million.
Exactly. If a user uploads a massive 100-page PDF and your app blindly sends it to a model with a small context window, the provider's server will reject it, drop the connection, and return an error. You've wasted bandwidth and latency for nothing.
So how does the proxy prevent that? How does it know the payload is too big before it sends it over the internet?
It requires enabling a specific parameter in the configuration called enable precall checks.
Enable precall checks.
Yep.
Yes.
When you toggle that to true, the architecture changes. Before LiteLLM fires the network request over the internet, it runs a fast, lightweight tokenizer locally on the proxy server. It physically counts the tokens in your prompt.
Wow, locally.
Yes. It then compares that integer against a configuration dictionary of known context limits for every model.
Oh, I see it. It is like an automated railway switchboard.
Okay, picture the railway.
The switchboard operator physically measures the length of the freight train while it is still in the station. If the train is 2 miles long, the operator doesn't send it down a track that ends in a 1-mile dead end just to watch it crash. They flip the switch and route it down the heavy-duty long-distance track.
That's a perfect analogy. If the local token count exceeds the primary model's limit, the proxy intercepts the request entirely and instantly falls back to a model you've designated with a massive context window, like Google Gemini Flash.
Which handles up to 2 million tokens.
Exactly.
And from a cost perspective, I imagine you can inverse this logic, right? You can use it as a budget enforcement tool.
Absolutely. You can define a custom max input tokens threshold on your expensive flagship models. Let's say you don't want any user sending a payload larger than 50,000 tokens to Claude Fable 5, because at $10 a million, those large calls burn your budget instantly.
Right.
If the local pre-call check counts 60,000 tokens, it blocks access to Fable 5 and routes the request to a dirt cheap model. It is automated financial governance at the network layer.
That is so powerful. And then, of course, you have the third category, which is just standard fallbacks.
Yes, which catches the mundane chaos of the internet. API rate limits exceeded, DNS resolution failures, standard 500 internal server errors.
Server timeouts.
Exactly. And because this proxy sits at the center of your infrastructure, you can implement highly complex routing behaviors. The documentation details wildcard routing, where you define your target as Azure.
What does the wildcard do?
The proxy will automatically load balance your requests across every single Azure deployment you have provisioned globally, hunting for the lowest latency.
Which is huge for compliance, too. The proxy can automatically handle EU region filtering. If your application handles European citizen data, the proxy can inspect the credentials and ensure that the request is only routed to physical data centers located in Frankfurt or Paris, right?
Yes, automatically inferring the region for Gemini or Bedrock, which ensures you don't violate GDPR by sending data to a US-based model.
That saves so much headache.
One critical operational note for the engineers listening, though. If you are implementing this, pay attention to how you test it.
Good point.
In older versions of LiteLLM, there were mock testing flags, where you could essentially instruct the software to pretend a failure occurred to see if the fallback triggered. Those mock flags are now deprecated.
Really? Why?
The developers realized that simulating network failures in software logic breeds false confidence. If you want to validate your fallback cascade today, you have to spin up a non-production environment and physically trigger real provider errors.
Like intentionally exceeding rate limits?
Yes. Intentionally exceed rate limits, revoke an API key, or sever a DNS route to ensure the proxy actually catches live network exceptions.
Okay, so LiteLLM gives us this incredibly powerful, self-healing routing layer. It lets us dance gracefully across all the major cloud providers, avoiding outages and minimizing costs. But let's push this architecture to its absolute limit. What if the cloud itself is the vulnerability? What if AWS US East 1 goes down entirely? Or what if you are a defense contractor or a healthcare provider and you have highly classified restricted data that legally cannot leave your physical building, no matter what compliance region a cloud provider promises?
You can't route to the cloud.
You have to pull the ripcord entirely and take the workflow offline.
This is the ultimate final stage of the exit ramp. Can you seamlessly migrate your highly complex agentic workflow onto bare metal servers that you physically own and control?
Historically, the answer was a hard no. The open source local models just weren't smart enough. They could write a poem or chat with you, but they couldn't reliably execute complex API structures.
And more importantly, the tooling was completely fractured. But the entire landscape of local AI shifted fundamentally with a specific software update early in 2026.
We are looking at the Ollama v0.114.0 release from January, right?
Yes. For listeners who aren't constantly tinkering with local models, Ollama is a massively popular open source application that makes downloading and running huge neural networks on your local machine as simple as pulling a Docker container.
You just type Ollama run Llama 3, and suddenly a localized AI is running on your GPU.
Exactly. But the version 0.14.0 update did something much more profound than just adding new models. They implemented native Anthropic Messages API compatibility directly into their local server.
To understand why this is revolutionary, we have to look at the tools developers are actually using right now. Anthropic recently released a terminal-based agent called Claude Code.
Yes. It is a highly advanced, autonomous tool that lives directly in an engineer's command line. You can tell it, read my code base, find the memory leak in the authentication module, write a fix, and run the unit tests.
And it will autonomously loop through those actions. It is an incredibly powerful productivity multiplier.
But the catch is that Claude Code is hard-coded by Anthropic to only communicate with Anthropic's cloud servers using their highly specific, complex API format.
It is completely locked into their ecosystem. If Anthropic servers go down, or if you are working on an airplane with no Wi-Fi, this critical tool stops functioning entirely.
Exactly. What the Ollama developers did was build a sophisticated translation proxy inside their local software. It listens on a local network port and perfectly mimics the exact responses and structure of Anthropic's multi-billion-dollar server farm.
So if I'm understanding this, it's like putting a mask on my local computer that makes it look exactly like Anthropic's servers. Mechanically, how do you actually trick the software?
It is shockingly simple. You do not have to rewrite the Claude Code application. You simply override two environment variables on your operating system.
Just two variables.
Yes. You set Anthropic auth token to Ollama, which bypasses the cloud authentication check. And then you set the Anthropic base URL to point to http://localhost.11434.
Port 11434 being the standard port where the Ollama service is listening on your local machine.
Correct. The moment you execute that command, Claude Code stops broadcasting out to the public internet. It sends its massive, complex payload to your local port, thinking it's talking to a massive cloud server.
And Ollama catches it.
Ollama intercepts that Anthropic formatted request, translates it internally, processes it through whatever open source model you have downloaded locally, and then formats the output exactly how Claude Code expects to receive it.
The implications here are staggering. You are taking a highly complex proprietary agentic workflow designed and engineered by one of the biggest AI labs in the world, and you are entirely severing its umbilical cord to the cloud.
You are running it on a locally owned GPU.
You have absolute cryptographically secure data privacy because 0 bytes are leaving your physical hardware, and you're paying $0 in recurring API compute costs.
It bridges the gap between cloud convenience and local sovereignty. But, and this is a big but, you have to pair this capability with a model that is actually intelligent enough to drive the vehicle.
Right, and this is where I have to heavily push back on the reality of this. I have run 20 billion parameter models locally on my laptop. They are great for summarizing a text file, but they hallucinate. They lose the thread.
They do.
You are telling me that a local model can handle the intense multi-step complexity of tool calling. Can a local open source model actually output the perfectly structured JSON schema required to trigger an external database query without dropping a bracket and crashing the entire application?
It is a totally valid skepticism because historically local models failed miserably at JSON formatting. But the architecture of open source models has crossed a critical threshold recently.
So the sources confirm they can actually do this now?
Yes, the release notes explicitly confirm this compatibility. Ollama recommends specific, highly tuned models for this exact task, such as GPT-OS.20b or the Qwen 3 coder models.
What makes those models different?
They have been explicitly fine-tuned on thousands of examples of JSON schemas and function calling structures. Furthermore, you need a model with massive memory context. The documentation notes you need at least a 32,000 token context window.
Why so much memory for coding?
Because an agentic workflow involves a massive amount of hidden back-and-forth communication. The agent writes code, reads the terminal error, rewrites the code, and reads the next error. All of that history has to stay in the local model's memory.
Ah, I see.
If you use a model with a 32K context window, like Qwen 3 coder, it can natively handle the streaming responses, the multi-turn conversations, tool calling, system prompts, and yes, the exact Flawless JSON formatting required to trigger external tools, mimicking Claude's capability almost perfectly.
That is wild. It means the exit ramp isn't just theoretical routing between cloud giants. You can genuinely drag a cloud-dependent enterprise system into an air-gapped concrete bunker if the business requirements demand it.
Exactly. So we now have the theory of cloud routing with LiteLLM, and we have the local fallback theory with Ollama. Now it's time to test it on a real business pipeline.
Let's do it. Let's put this into practice. The blueprint we are examining outlines a phenomenal engineering exercise called the Delete One Tool stress test.
I love this methodology. It strips away all the theoretical architecture diagrams and forces an engineering team to confront the brutal reality of their technical debt.
The exercise works like this. You map out your core AI pipeline onto a whiteboard. Let's invent a hypothetical but very realistic company. Let's say we run a SaaS platform that generates automated legal contract summaries for law firms.
Okay, legal tech startup.
We can break our technical pipeline down into 5 distinct sequential stages: source, context, model, output, and storage.
And as we evaluate each stage, we apply a strict grading matrix. We label components as green, yellow, or red.
Define the criteria for those grades for us.
A green grade means the component uses entirely open standards and is immediately replaceable. You have zero vendor lock-in. A yellow grade means you are utilizing a third-party service, so migration will be required if they shut down, but you own the underlying assets.
It might take 1 to 3 days of painful engineering effort to migrate, but the business survives.
Exactly.
And a red grade.
A red grade means catastrophic workflow failure. If that specific vendor disappears or quadruples their price, your workflow halts immediately and you lose critical data because it is locked in their proprietary format.
Okay, I am going to play the role of the stressed out CTO of this legal summarization startup, and you are going to audit my architecture. Let's run the pipeline.
Let's begin at the source phase. Before the AI even touches a legal contract, where do the raw, original PDF and Word documents physically reside?
Well, we take client confidentiality seriously. All the raw contracts are stored on a secure, air-gapped local database cluster in our main office, and they are regularly backed up to encrypted external storage arrays.
Excellent. That is a solid green. You maintain absolute sovereignty over the raw data. No cloud provider can revoke your access to the foundational files.
Wait.
Now, we move to the context phase. When a lawyer asks the AI to find a specific liability clause across 10,000 contracts, you aren't sending all 10,000 PDFs to the LLM at once. You have a retrieval augmented generation system. How is that built?
Right. We take all those local contracts and we run them through an embedding model to convert the text into mathematical vectors. We then upload those millions of vectors into a proprietary managed vector database cloud service, something like Pinecone or a managed cloud instance. That database handles the incredibly fast similarity search.
I'm grading that as a yellow.
Really? Why?
Here is why. The managed cloud vector database is highly efficient, but it is a dependency. If that cloud provider suffers an outage, or if they abruptly triple their hosting fees, your search functionality goes offline.
But it's not a red because I still have the original PDFs on my local servers.
Correct. You haven't lost your business. But migrating is computationally expensive. You cannot easily extract raw vectors from many proprietary systems.
So if they shut down,
Your engineering team would have to spin up a new open-source vector database like Milvus, or a PostgreSQL instance running the PG vector extension. You would then have to take all your local PDFs and spend perhaps 48 hours running massive compute clusters to completely re-embed and re-index the entire dataset from scratch.
oh wow.
It is a painful, expensive weekend for your engineers, but the business survives.
Okay, I can live with the yellow. Let's move to the model phase.
Okay.
This is the core reasoning engine. To generate the actual summaries, our Node.js backend has a hard-coded OpenAI client SDK installed, and we are making direct API calls specifically targeted at an older, stable version of GPT-4.
That is a glaring, catastrophic red.
Yikes. Explain the exact mechanism of the failure.
You have tightly coupled your core business logic to a proprietary SDK and a specific model ID. If OpenAI decides tomorrow morning to deprecate that specific older version of GPT-4, which is their standard operating procedure to free up GPU compute, your backend code literally breaks.
It just stops.
The API endpoint will return a 404 error, the SDK will throw an unhandled exception, and every single request on your platform will fail.
Cool.
Your customers will see blank screens, you are down until you write new code test it, and deploy it.
Okay, as the CTO, how do I immediately remediate that Reddit? How do I build the exit ramp for the model phase?
You deploy the architecture we just discussed. You rip out the direct OpenAI SDK from your code base. You replace it with a generic HTTP request pointing to a LiteLLM proxy server deployed within your own VKC.
Oh, okay.
You configure the proxy to use a modern, cost-effective model as the primary, but you build out that robust fallback cascade. You configure secondary routes to Anthropic, to Google, and perhaps even to a local Ollama instance running a summarization model. You completely abstract the vendor away from your application logic.
That makes total sense. I am insulated. Now let's look at the final stages. Output and storage. Once the AI generates this beautiful, highly accurate legal summary, how does the user actually see it?
How do they?
Well, currently, our users log into a custom GPT interface that OpenAI hosts. They view their summaries inside that web portal, and they organize their cases using the folders provided in that UI.
That is the deepest shade of red possible. It is a fatal flaw in the business model.
Guy, we are saving so much time on front-end development.
Because you do not actually have a software business. You are merely leasing a feature from a trillion-dollar company. If your users are interacting with the data exclusively inside a vendor-owned interface and the output is stored in their proprietary cloud database, you own nothing. If the vendor suspends your account for a terms of service violation, or if they decide to pivot their UI entirely, you lose the historical output of every summary ever generated.
We can't export it.
You cannot export that data cleanly. You have zero leverage.
Man, when you lay it out sequentially like that, acting it out, it is a chilling realization. I thought I built a tech company, but my business logic is completely trapped.
To fix that red, you must enforce open formats at the storage layer. Your workflow middleware must intercept the AI's output, extract the raw payload as standard Markdown or JSON text, and forcibly export it to a self-managed object store.
Like an AWS S3 bucket we control, or a local network-attached storage drive.
Exactly. And crucially, you must build your own front-end web interface to present that data to the user. You own the glass they look through.
If we connect this to the bigger picture,
Right.
running this delete one tool stress test isn't just an exercise in disaster recovery for a paranoid IT department.
Got it all. It is fundamentally an audit of enterprise value. When venture capitalists or potential acquirers look at your company during due diligence, they are looking at this exact pipeline. If a vendor owns your architecture, from the prompt injection all the way to the output UI, they effectively own your business. You have zero enterprise value because you have no defensive moat, no proprietary infrastructure, and no sovereignty over your operations. You are easily replicable and highly vulnerable.
It's a huge wake-up call. But let's pivot the conversation here, because doing the hard engineering work to achieve a completely green pipeline isn't just about risk mitigation, safety, and impressing auditors. It actually unlocks massive, immediate, aggressive financial leverage.
It does.
And I want to circle back to the numbers, because the math here is staggering.
Portability is the absolute prerequisite for cost optimization. You cannot play the market and hunt for arbitrage opportunities if your feet are glued to one vendor's floor.
Let's revisit that 100x pricing spread we talked about at the beginning, but let's take it out of the abstract realm of token math and apply it to specific real-world business tasks.
Okay, let's look at the data.
The Cloud Insight Guide gives us incredible data here. Let's look at scenario 1 from their report. Generating a 1,000-word summary of a Chinese document. They map this out as requiring roughly 3,000 input tokens to read the document and generating 1,500 output tokens for the summary.
A very standard high-volume enterprise task.
Right. If your architecture is fragile and you are hard-coded to route that task to Claude Fable 5, which is a phenomenal top-tier model, that single generation costs roughly 10.5 cents.
Which doesn't sound like a lot.
No, 10 cents is nothing. But if you have the resilient architecture and your LiteLLM proxy routes that exact same task to Google's Gemini 2.5 flashlight, it costs a fraction of a penny, specifically $0.009. That is the 100x price difference realized on a single API call.
And you have to extrapolate that across scale. If your platform is processing 50,000 of those summaries a day, the difference between a 10-cent cost and a tenth of a cent cost isn't just a budget line item. It is the fundamental difference between building a highly profitable, self-sustaining business and declaring bankruptcy because your unit economics are inverted.
Let's look at a heavier workload. Scenario 2. Analyzing a 50-page PDF document, pulling out key metrics. This is intensely heavy on the input side. They assume 100,000 input tokens to swallow the whole PDF and a small 2,000 output token response containing the extracted metrics.
If you are sending that to Fable 5, you're paying a $1.10 for every single analysis.
Hmm.
If a user uploads 10 PDFs, that's $11 gone instantly.
But if your proxy routes it to Gemini 3.1 Pro Preview, the cost drops to 22 cents, and if you route it down to Gemini 2.5 Flashlight, it plummets to just over a penny.
And the source material highlights a critical engineering advantage regarding the Gemini Pro models here, the context window. They boast a 1 million to 2 million token context window.
Why does that matter for the PDF?
In older architectures, if a user uploaded a massive PDF, engineers had to write complex, brittle code to chunk the document into smaller pieces, send them sequentially, and then try to synthesize the results. With massive context windows, you just pass the raw document into the proxy, saving countless hours of developer time and reducing application complexity.
But the math flips when we look at scenario 3, which is generating Python code. Here, the output tokens heavily dominate the transaction. The prompt might be short, say, 1,500 input tokens saying, write a script to do X. But the model spits out 3,000 output tokens of code.
And because output tokens are inherently 2 to 5 times more expensive across the industry, the premium models will absolutely annihilate your budget here. Generating that code on Fable 5 costs roughly 16.5 cents per run.
But if you route it to OpenAI's newer, highly optimized GPT 5.6 Luna model, it costs only under 2 cents.
The Cloud Insight Guide provides a really clear breakdown of the GPT 5.6 family to illustrate this optimization. You have Sol, their massive flagship reasoning model, sitting at $5 input and $30 output. You have Terra, the balanced mid-tier model, exactly half that price. And then you have Luna, the high-speed value pick, at just $1 input and $6 output.
The overarching lesson here is that there is no magical one model to rule them all API. The longer your required output, the more the output rate dictates the financial viability of the task. If you want to survive, you must deploy intelligent routing.
Which leads us directly to the 5 strategies to save on APIs outlined in the source. How do we operationalize this financial leverage?
Strategy 1 is task routing, and this acts as the capstone for everything we have discussed today. You must classify the complexity of your prompts dynamically.
If a user requests a simple classification or a translation, the proxy routes it to a Nano or Flashlight model.
Right, keep it cheap.
If they need standard text generation, it routes to Sonnet 5 or Luna. You only ever authorize routing to the massively expensive Sol or Fable 5 models when the task requires deep, complex, multi-step logical reasoning.
But from an engineering perspective, this is the entire point. You can only implement strategy 1 if you have successfully built the resilient architecture and deployed the LiteLLM abstraction layer. If your Node.js app is hard-coded with the OpenAI SDK, you can't route anything. You are forced to pay the maximum premium price for every single network call, whether the AI is solving a complex mathematical theorem or simply capitalizing the letters in a user's name.
Portability is not just disaster recovery. Portability is the mechanism of cost optimization.
Let's hit strategy 2, because this is an architectural feature that completely blew my mind. Prompt caching.
Caching fundamentally alters the economics of heavy API usage. When you send a massive system prompt to an LLM, the GPUs have to perform intense mathematical computations to process those tokens into memory. Historically, you paid for that compute every single time you hit the API.
But now, providers like Anthropic and OpenAI allow you to cache that prompt in the GPU's VRAM.
Yes, Anthropic's prompt caching can save you up to 90% on the input cost for repeated system prompts.
90%.
Yep. OpenAI's caching architecture saves roughly 50%. If you have a massive 10,000-word set of instructions defining the behavior of your customer service bot, and you send that exact same context payload with every single user message, caching means you only pay full price the very first time.
Every subsequent call hits the cache, and your costs plummet.
Exactly. The market data report actually notes that because Anthropic's caching discount is so aggressive, it often makes Claude cheaper than OpenAI in real-world production environments for applications that rely heavily on massive static system prompts.
That is an incredible detail that you only discover if you aren't locked into one vendor.
Right, you'd never know.
Strategy 3 is batch processing. This requires an asynchronous architecture. Both OpenAI and Anthropic offer a massive 50% discount on the total token cost if you submit your tasks as a batch file and accept a 24-hour turnaround window rather than demanding immediate real-time streaming responses.
If your business is summarizing a back catalog of thousands of historical legal briefs, you should never process that synchronously. You batch it, submit it, and cut your bill in half.
Strategy 4 is just basic engineering hygiene, but it's shocking how few startups do it. Monitor your usage and set hard algorithmic budget caps.
Oh, please do this.
Configure your proxy to fire alerts to a Slack channel when you hit 80% of your daily budget limit. Do not let a rogue infinite loop in your code silently rack up a $50,000 AWS bill overnight because a user figured out how to trigger recursive generation.
And finally, strategy 5 is utilizing enterprise reseller discounts. If you reach a certain scale, you shouldn't be paying the retail sticker price listed on the website.
Right, this is where organizations like Cloud Insight come in. If you are burning millions of tokens a day, you route your procurement through a bulk reseller. They negotiate discounts below the list price.
And practically speaking, if your company operates in places like Taiwan or the EU, these resellers handle the complex local tax invoicing and compliance requirements, which drastically simplifies procurement for your finance department.
So when we synthesize all of this, the routing, the caching, the batching, what is the ultimate takeaway for the architecture of a modern AI company?
What do you think?
It makes me think of an analogy. When you step back and look at the whole picture, having an AI exit ramp isn't just a defensive, paranoid IT posture. It is a highly aggressive, strategic business advantage.
I agree completely.
It's like having a universal fast pass at a massive, chaotic theme park. While all of your competitors are stubbornly stuck in a 3-hour line for the one specific roller coaster they are loyal to, you have an automated system that is constantly scanning the park.
Hunting for efficiency.
Exactly. It dynamically routes you to the cheapest, shortest line for the exact caliber of ride you want to experience. And if a ride breaks down mechanically, your system instantly diverts you to a backup ride without you ever breaking stride. You get 10 times the output for a fraction of the cost.
That is a flawless summary of what a resilient AI workflow looks like in production.
We have covered an incredible amount of technical ground today in this deep dive. We started by confronting the raw volatility of the AI market, the overnight price spikes, the silent model deprecations, the 100x pricing spreads, and the deceptive token math that inflates your bills.
We broke down the critical differences between fragile, hard-coded architectures and resilient, abstracted systems.
We explored the computer science behind reverse proxies, showing how LiteLLM intercepts requests to build a self-healing, multi-provider network. We looked at how Ollama's ability to spoof API ports locally allows you to pull the ripcord and take complex agentic workflows completely offline.
And we proved, through the stress test and the scenario modeling, that vendor portability is the ultimate cost-saving strategy.
So I want to address you, the listener, directly. Tomorrow morning, call a meeting with your engineering team. Run the Delete One Tool stress test on your core product. Look at your code base. Is your core business logic hard-coded to a single model's proprietary SDK? Are your prompts locked in a vendor's web portal? If your primary AI provider changes their rules, raises their prices, or suffers a catastrophic outage on a Tuesday night, do you have an exit ramp?
And I will leave you with one final, perhaps deeply provocative thought to consider as you audit your systems. We have spent this entire time talking about how to rescue your workflow if your AI vendor suddenly disappears or fails. But consider the inverse scenario.
The inverse.
What if the vendor doesn't disappear? What if instead they look at the massive daily volume of highly structured workflow data you have been happily feeding through their API for a year? What if they realize exactly how valuable and lucrative your specific business process is, and they decide they are now your direct competitor, launching a native feature that does exactly what your startup does? If you do not control the exit ramp, and your data is hopelessly locked inside their ecosystem, you might just be paying them to train your own replacement.
And suddenly, that abstract architecture diagram on the whiteboard becomes a matter of absolute corporate survival. Build the exit ramp, abstract the API, stay resilient. We'll see you next time.